One of the most useful prediction tools in mathematics, or you could maybe even say in statistics, is the construction of mathematical models from real-world data. One of the methods used to develop such models is called the method of least squares. And I'm going to show you why this works for what's called a line of best fit. Suppose we have a set of data points x1, y1, x2, y2, up to x sub n, y sub n, and we wish to find, what we want to find is a function that has a straight line, y equals ax plus b, a being the slope, b being the y-intercept, that best fits the data as in the picture below. The purple dots are my set of data, and the blue line is, or maybe that's the black line. Yeah, sorry. I don't see color all that hot. So this black line is the line that best fits that data, supposedly. And the little blue amounts are how much it misses by, okay? So the data is the purple dots. The blue lines represent the difference between the data point's y value and the predicted y value from the linear function y equals ax plus b. So these blue lines are those differences between the predicted y. In other words, at this point, this would have been the predicted y by the line, but the actual data was here. Similarly, over here, this is the actual data, this is the predicted data right there on the line. So, turns out if we just added up these differences, all those blue lines, we always get 0 as long as the line passes through what's called the centroid x bar, y bar, where x is the average x and y is the average y, or y bar is the average y value. So the least squares line minimized the function of two variables, s of a and b. Keep in mind we're trying to find a and b, where f of xk is the value of the computed function and y is the data point's ordinate. And so we're going to square these differences and then minimize that set of squares. So here's our function s of ab, and that's equal to f of x sub k minus yk squared. So in other words, the f of xk from our line would be here, and the yk from the data would be here. So we're minimizing the squares, those blue lines squared. And so if this is our function of two variables, and we're trying to find the minimum of this function, the very first thing we would do would be find the partial with respect to a, the variable a. And of course, since this is a constant and this is a constant, it would be 2 times this expression times the derivative of the inside function, which is just x of k. That's the derivative with respect to a. The inside function would just be x of k. So there you have it. That's the partial with respect to a. See if you can work out, before I just scroll down a little bit, what would the partial with respect to b be for this one? Well, it would be 2 times this times 1. So here it is, 2 times that. And now this thing, the partial with respect to a, I could algebraically simplify a little bit by distributing. So we get the a, since we have an a that's part of this term, I factor out the 2 in the a times the partial, I'm sorry, not the partial, but x sub k squared. Remember, a is the variable, xk is a constant, so it's the sum of all those. 2b, we factor out of the next term with an xk in it, and then finally minus 2 times xk yk, this xk, this yk. So that's our partial with respect to a. Our partial with respect to b, I think we already described what that is. And that can be simplified by factoring out the 2a, which is constant, and then, well, actually it's not constant, but it's part of each term, so times the sum plus 2 times n times b. Now if you're wondering where that came from, if we added up from 1 to n all these b's, it would be n times b, but then times this 2. We got 2nb, and then minus this sum of the yks. But there's 2 of them, so there that is. So both of these, that's SB, I'm getting it there, it is that, and our SA, we want those to be 0. And for each data set, each of the summations is just a number. So this is a number, this is a number, this is a number, this is a number, this even is a number. So therefore, if we want to set the partial with respect to A equal to 0, it's 2A times this number plus 2B times this number minus 2 times this number. Each of these numbers are computable. And so let me see. And since partial with respect to B also has to be 0, then all this has to be 0. This is 2A times this number plus 2 times n times b minus 2 times this number also has to be 0. Simplifying this mess, you get A times this number plus B times this number equals this number. That's the simplification version of this one. And simplification version of this one would give us that A times this sum plus NB is equal to this sum. Keep in mind, all these summations are just numbers, so we have a number times A plus a number times B equals a number, and this one says a number times A plus a number n times B equals this number. So, using Kramer's rule to solve for A, the variable, we have the easier to do the denominator first. The coefficients of A and B are matrix coefficients, this one, this one, this one, and this one in our denominator. And when we want to find A, we replace the A column with the answers on the right. And so that means this number times n minus this number times this number, and here that is, divided by this number times n, see, minus this number times this number, they're the same, right, is equal to our A. So that gives us a formula for solving and finding the slope of the line. Remember, each of these is just a number. And so, and if you solve the second equation for B, this one, B equals this sum minus this sum, actually I have to fill in the A and then divide that by n. And so if you solve the second equation for B, you get the A that we've calculated here. Well, you can probably go back and follow that and say, oh, darned if we don't get this value for B. So all of this leads to, and is really the proof of, the following theorem about the least squares regression line. Okay, so here it is, theorem 13.8, the least squares regression line. The least squares regression line for the set of data points x1, y1, x2, y2, dot, 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 up to xn, yn, is f of x equals ax plus b, where a is the slope, and it can be calculated by our Kramer rule example above, and b equals, substituting that in for the b, is this expression. 1 over n times the sum, k going 1 to n, yk, minus a that we calculated up here, times the sum, k going from 1 to n of x sub k. Remembering, each one of these is just a number that can be calculated from our data point. Okay, it would be prudent to solve for A first because that's part of the answer for B. Right here it is. Because, ooh, nice spelling, huh? Because that value is necessary to compute B, and note 2, most graphing calculators and even some older scientific calculators have not only the least squares regression line, but other functions of best fit as well. Some other commonly used function models are polynomials such as quadratic polynomials, cubic polynomials, logarithmic equations, and exponential models. But they all do use the concept of least squares to find the function that's best fit. So you have to read your calculator's manual to explain how it's done and what the computed parameters are called. Great. I might mention before going on, finding the line of best fit is always a part of almost every statistics class. So we'll look at another example here in just a second.
I can't wait.
All right, and the example of a least squares line, or maybe even a cubic or quadratic, I think we're going to use, should be interesting.
I agree.
I'm glad.